Welcome everyone. Today I'm going to talk about how to build reliable stateful services by taking advantage of data centers environments to improve fault coverage and to reduce the operational cost. So this work was done with my advisor, Rodrigues, and João Leitão from Nova University of Lisbon, Cheng and Alan Clement from Max Planck Institute, Aniket Kate from University of Zeeland, and Flavio Junqueira from MSR Cambridge. So let's get started. So data centers has a high level of availability, you know that. But the reality shows that when they still fail, and when they do, it impacts on revenue. So when Facebook went down in 2012 for 2 hours, it was worldwide, the stock price dropped by about 6%. And in a more recent outage that lasted for 20 minutes, it cost like $500,000. So data center outages matter. What are the causes of these outages? Well, faults can cause outages, but misconfiguration and operational errors too, but they're not the focus in this talk. So to provide, in order to tolerate those faults, systems employ distributed fault tolerance protocols, and they play a key role as they allow the system to continue to operate even in presence of faulty components. So protocols are designed according to to capture some class of faults, for instance, crashes. And if the faults and the fault not captured happened, then the correctness of the system is at stake. So, and moreover, to change the protocol to be able to capture those faults is not always a simple task, and normally it may require a complete redesign of the protocol. And also, protocols assumptions are not always easy to get right. First, because it impacts on replication factors if the assumptions are too broad. And on the other hand, it may put the correctness at stake if they are too restrictive and very difficult to meet in practice. But fortunately, there are many advances in data center technologies which makes these environments much more predictable than the wild internet. So as evidenced by recent work published in important conferences like NSDI, OSDI, EuroCIS, and TICCOM, that spans in many areas, from data center networks, scheduling, management, and even operating system. So we believe this trend is likely to continue. Another way in which data centers are more predictable is regarding the security. They all have security measures to protect or even limit the exposure of the system for an outsider and attackers. So therefore, it is considered unlikely that the worst adversarial behavior, such as a malicious attacker corrupting messages to defeat the system, will happen. However, given the scale in which these systems operate, even these faults that are considered unlikely, they surface. So in 2008, Amazon had an outage in S3 servers, and the cause was found was a message that was corrupted in a way that the message was still readable, but the state was corrupted. And that the cause was a single bit flip. So, given this observation, we can ask the following research question. So, can we leverage the increased predictability of these data center environments to lower replication cost while decreasing the downtime? Well, to understand how that can be done, we observed the today widely used protocol, specifically the most robust ones. So they somewhat are pessimistic regarding the assumptions in several dimensions. So regarding timing, these protocols are designed assuming full asynchrony, like the environment like the wider internet, in which all the message and processing times could be arbitrarily delayed. And regarding faulting behavior, these protocols are designed to tolerate either crash or malicious or coordinated malice, which is captured by the Byzantine model. But BFT is not used in practice, and instead, the designers normally use CFT plus ad hoc solutions, such as adding digest to protect the state. And so, to build more reliable resource-efficient protocols, so our approach is to take advantage of the predictability of these data center environments in order to make these protocols less pessimistic. And that can lead to savings compared to asynchrony, and therefore lower resource requirements for protocols such as Paxos. And also, we take advantage of this increased security to increase the fault coverage by capturing faults that are non-malicious arbitrary faults, but not non-malicious, without incurring in the full cost of a full-fledged BFT approach. So, and to answer this question, we believe this, yes, is possible. And to achieve that, I will present to you Visigoth Fault Tolerance. So in a nutshell, Visigoth Fault Tolerance is a new technique for designing a distributed protocol for reliable and stateful services. So the Visigoth Fault Tolerance introduced the Visigoth model, which provides you a knob that enables you to calibrate the system according to the environment. So it was named after the kingdom of the Visigoths, which eventually extended from Lisbon, where I work, all the way up to Bordeaux, where we are now. So in the rest of my talk, I will focus on the definition of the Visigoth model and why we think this is the case for data centers, and how we apply this in practice with a technique that allows to cut replication factors and while reducing the downtime by being able to capture a broader class of faults. So the Visigoth model provides you, enables you to calibrate the system according to the environment guarantees. So regarding timeliness, it allows to capture strong guarantees, such as the synchronous system, which will have a very tight deadline that should be met. But also, it also is able to capture full asynchrony when you have no assumption about no guarantees whatsoever. But also, it also captures a middle ground with different levels of partial synchrony. In the dimension of fault behavior, it also allows you to capture crashes, such as the Death Star killing a process and no action can be taken after it. But also, it accounts for collusion, like adversary controlling components at will, and also the middle ground, like arbitrary but not necessarily malicious faults. So a quick question of this model is, how do we precisely capture the middle ground between each one of these categories? So let's first focus on timeliness. So we know that network is asynchronous. That can delay, reorder, drop messages. However, data centers, there is a number of technologies that enable predictability, everything, and the performance is, and therefore, we think that it's reasonable to expect that most of the time, the message will be delivered timely and in the timely fashion. So in Visigoth model, we say that among all the processes, the communicating processes, there is a subset of the process that can communicate timely. And by timely, we mean that the message should be sent and received within a T time bound. And there is a limited number of processes that can be perceived as slow. And we encode this parameter and we code this assumption in a parameter called S. So what is interesting here is that in a communicating process, among all the messages that you didn't receive, there is a mix of crash processes and also slow processes, but we don't need to pinpoint which one is slow or crashed. So to validate whether this assumption makes sense, we conducted a measurement study. So we deployed a measurement study of a group of processes in Amazon EC2, and in these groups, each process sends out a RPC call to all participants to emulate an RPC-based distributed protocol. And they measure the RTT. So what we see in this graph here is a complementary CDF to aggregate about 3 million messages for a group of 7 processes. So each line represents the latency to receive the first, the second, the third reply, and so on. What is interesting here to see is that if we could afford to not wait for the last reply, let's say we can receive 6 replies, in 99% of the time, we could select a timer like 100 milliseconds. So 100 milliseconds will suffice to receive all 6 replies in 99% of the time. So we are not claiming these results are general. We're just saying that, giving some example of how one could select the S parameter and the T parameter in the Visigoth model. So for different protocols or applications, as we saw with different data center technologies, so a similar study could be done. So now let's shift our attention to the Visigoth, how does the Visigoth model captures the middle ground between crash and malicious faults. So the goal here is to capture non-malicious data corruption that stems from transient hardware faults, such as bit flips and memory corruptions. So in Visigoth model, we say that the processes can crash or suffer a non-crash fault and output incorrect messages. So all this universe of messages are captured by the parameter f. And however, there is a limited number of messages that could be correlated, in the sense that you can have arbitrary corruption, but if you're really, really unlucky, those arbitrary corruptions could map to the worst case, to the worst that may look like the worst adversarial behavior, and and may look like they are colluding. And is that apparent collusion or coordination that we are bounding here? So the next question then is, what do we mean by correlation? So by correlation we mean that the message has the same type. So in the state machine protocol, for instance, it would be the number of messages that you need to receive to trigger a view change. So to summarize the parameters of the Visigoth model, so there is a parameter t, which is the max delay to transmit and process message, but it does not need to hold all the time. There is a bound on which is s, on the max number of processes that can be perceived simultaneously as the slow, which means that they don't, the messages are not received by the time t. There is a bound on O, which is the max correlated commission failures that you are allowed to have, and a bound on F, which is the maximum number of faults. So next, I will talk about how we apply VFT in practice and to show you some results. So we choose to apply VFT on consensus because it's an important problem and is at the core of many replicated stateful services. So we prove a lower bound, which is the one that we're seeing here, but I'm not going to this detail. So if you want to see the proof or more or detailed information, so you can refer to the paper or a separated TR. But what is interesting here is that for the special case where F is greater than S, so this inequality could be simply rewritten as F plus S plus O plus 1, which contrasts to BFT 3F plus 1. So that means that it grows slowly as you want to increase the number of captured faults in the system. Or the size of the system grows slowly if you want to increase the number of captured faults in the system. So another interesting result in Visigoth model is that it provides you a sliding window between the traditional models. So first, let's just consider crash faults. So in the x-axis here show the number of slow processes that one can see in the system. So for s equal to 0, it means that no process can be slow, so therefore you are in a synchronous system, synchronous model. For s equal to n, all processes can be slow, so therefore the system is fully asynchronous. So then if we look at the inequality, it reduces down at the limits, it reduces down to the classic result, the synchronous CFT, where the bound is n equal to f plus 1, and fully synchronous CFT, which is 2f plus 1. So now let's bring back the arbitrary fault into play. So similarly, for O equal to 0, it means that no process can commit arbitrary faults. And when O equal to F, what we see that all arbitrary faults could be correlated or could look like they are collusion. Then again, looking at the bound, it reduces down to the classic results. So the synchronous BFT and also asynchronous BFT. So however, VFT allow more configurations that enable you to fine-tune the system according to the different environment guarantees. So it's not only the extremes. So, and of course, no token replicated protocols could be complete without a extremely complex timing diagram that I will explain in very high level of detail where you all fall asleep, especially after lunch. So the KGP protocol, okay, so I'm just kidding. I'm not talking to that, so not right now. So what we want to show here is how we show how does the Visigoth model works and save by simply using quorums. So, but before getting to that, let's first try to understand why does Paxos need two f+1 replicas. So in Paxos, a client sends a proposal with a value to a group of processes to agree. In this scenario, we are using two faults. So let's first assume that A sends out a value V1, but only A, B, and C receive it. So since processes A, B, and C can communicate timely. So at this point, we need to be able to make progress because the remaining F processes might have crashed, and therefore they will never reply. So thus the quorum size of f+1 suffices, and then the process can make progress and finally decide. But let's suppose that this process didn't crash. So instead, they're just slow, and a concurrent process E sends out a value V2, but only E and D receive it. So because they need f+1 message in order to make progress, they have to wait for one of the processes in the other group to respond. But however, this member is guaranteed to have seen V1, and because the majority intersects, and thus it will not allow any contradicting value. So now I will explain you how does VFT allow you to cut 20% on replicas while we still tolerate the same number of faults. So in contrast here, so we use only 4 replicas to tolerate 2 faults by setting S equal to 1. So, which implies that we need to be able to make progress with only 2 other replicas because the remaining ones may have crashed. But this raises the question, this is not a majority, so how can we ensure intersection? So by the model assumptions, at most one process can be slow, and therefore the other process must have crashed. Or both processes have crashed. So thus, any quorum that is formed must participate, that is formed, that slow process must include at least one timely replica, and that the stronger assumptions is that the guarantees that this quorum intersects and no other value could be accepted. So, but what would happen if we have a partition? Well, when these assumptions are not met, perhaps this safety might be at stake, but we extended the model to address this scenario. So when we have a partition, what we have here is that A and B could be in one side of the partition and C and D in the other side. So in that way, A and B may think that at most one process is slow and the other one must have crashed, and then it can make progress with only 2 replicas. At the same time, C and D may think the same thing. Okay, A and B, one of them have crashed and the other one is just slow, so I can make progress with just 2 replicas and perhaps make progress with different value. So to prevent this kind of behavior, we extended the model with an oracle that is responsible to select which partitions should make progress. So in some sense, it brings back majority. However, it does it in a very efficient way because this partition selection, it only happened in the very first step of the protocols and does not need to be done all the time. And because the oracle could be used by many, many Paxos groups, then the cost of having it could be amortized. So now I will talk about a few details about the implementation and how we evaluate and some results in the evaluation. So we implemented VFT by extending a popular open source BFT library called BFT Smart. And the main changes were basically adapting the protocol to use the VFT primitives and adding a layer to control the timers. So you need to know when you are able to make progress with a smaller quorum. So the oracle was implemented using Zookeeper, but you could use another thing to implement it, like a full-fledged BFT. And then we performed an evaluation. So comparing BFT with VFT for the same value of F, what we see here is that VFT have a better performance because it uses fewer replicas. And therefore, it has to wait for less message and there is less message to be processed. However, when we compare with CFT here, so there is an opposing effect. While the VFT allows you to lower replication factor, as the load increases, VFT has to manage and process and reset and set many timers. And as a result, it affects the performance, and it turns out better for CFT. But the timing management could be optimized and for a better performance. This is not particular for the model itself. Looking at another dimension, when computing the cost of each operation based off the max sustained throughput that one can have and prices from Amazon, what we see here is that VFT is much more cost effective because it improves on BFT Smart at least 109% and up to 159%. And even comparing with CFT, it improves in 79% due to lower replication requirements. So, in a nutshell, the pessimism impacts on cost, but data centers are not that bad. And what VFT captures is enables you to choices between a more conservative approach or a more optimistic according to your environment's characteristic, and also to capture faults that happen at the scale, which results in saving in operational costs. So with that, I conclude my talk, and I'll be happy to take questions.
So sorry if I misunderstood. Are you using the Zookeeper Oracle only when to break ties, or are you using it every time you need to change the data?
No, it only kicks in the beginning. When you don't have enough replicas to make progress and you know that your system cannot guarantee those tight deadlines, then you just, the first group, for instance, contacts Zookeeper and is configured, and then the other one, the second one, for instance, if you try to take a step, it has to contact the Oracle. But the Oracle knows that it already gave, for instance, the token to the other group. So only one, it's used only on that time.
Okay, so it wouldn't be simpler to just always use the Zookeeper Oracle? Okay.
No.
Ed Bugnon, EPFL. So I just want to go back to the point that you make that the data center is not that bad. Maybe I spend too much time in data centers. They're getting, in many ways, extremely complex. If you compare the data centers today from the era in which PBFT, BFT, Paxos, and all these other systems were designed, we have a much higher degree, much greater numbers of levels of indirection on the compute side with virtualization, on the network with SDN. We have dynamic resource management that is becoming more and more aggressive, that introduces a degree of variability. So the underlying assumption that's motivating this work is one that I was wondering if you could expand on, because you can also very clearly make the contrarian argument, which is that data centers are getting denser, more efficient, but at the same time more variable.
Yes. So, and what is nice about this work is actually to allow you to calibrate for these different kind of environments. So if you were to deploy this in an environment that you cannot guarantee those assumptions, and then it just make a conservative approach. You can always fall back to setting S and F to the maximum limits, and therefore you basically end up with the traditional bounds. So, and as you see how your system perform, you could tune it down, and therefore saving costs.
Hello, Malte Schwarzkopf from University of Cambridge. So you had this T parameter, and maybe there's a detail that is in the paper and is omitted in the presentation for simplicity, but the capital T parameter didn't seem to occur in many of the formulae later on. Could you maybe explain the significance of it? And the reason specifically that I ask is because we have some upcoming work published in NSDI in 2 weeks' time where we basically, for a limited number of messages per second in a data center setting, can give you a hard upper bound on latency. So if I understand your model correctly, we could set the value of S to 0 because none of the processes are arbitrarily slow because we have a hard upper bound. But of course, T is affected because that hard upper bound, while a hard bound, is still a number that's larger than the average latency.
Yeah, I mean, that's a good question. So there is a relationship between T and S. So when you define S, for instance, when S equal to F, so T is basically going to infinity. So there is a relationship on that. So this is why we should...
Oh, so you define S as any process that has not responded within the timeout T.
Yeah. So it's not a direct relation. It's something that you can use to derive...
No, I get it now. Thank you.
Okay, well, one more question.
Okay, I didn't completely follow your protocol. I was just wondering, are you using timeliness for safety, or this is just for progress?
For both. We also use it for progress. So...
use it for safety.
Mm-hmm.
Yeah, people usually try to avoid doing that, right?
Yeah.
Okay, thank you.
Thank you.